Hi, here we're going to talk about aldehydes and ketones. And in the last chapter, we talked about the carbonyl group. And remember, the carbonyl group is this carbon that is bonded to the oxygen. So it's a carbon-oxygen double bond. So a carbonyl compound is any compound that contains a carbonyl group. Carbonyl groups are strongly polarized, and remember what you have: a carbon bonded to this oxygen. The oxygen is more electronegative, so that draws the electrons towards itself, and this creates a partial positive charge on the carbon and a partial negative charge on the oxygen. So it's the polarity of the carbonyl group that contributes to its reactivity. The carbonyl carbon, as you can see, is surrounded by three electron clouds, or three regions of electron density. These bond angles are about 120 degrees, and this is a planar triangular molecule. Remember, our alkanes, right, where you have a carbon bonded to four hydrogens, okay, these bond angles here are 109.5 degrees, and that makes the carbon in an alkane a tetrahedral carbon. And then we talked about the alkenes, okay, so we have this double bond between the two carbons. And let's look at this carbon here, okay, it's bonded to three groups, and again, what we have is a trigonal planar geometry about that carbon, and these bond angles are also about 120 degrees. So just like with the alkenes, this carbonyl group here has the bond angles of 120 degrees, and the carbon is trigonal planar. We can divide the carbonyl compounds into two different groups. Here we're going to talk about the aldehydes and ketones, and then later the other group, carboxylic acids, esters, and amides. So let's take a look at these groups. This is a table that I got from another book, but here we show the aldehydes and the ketones. Okay, again, this is what we're going to talk about in this video. And later on, we'll talk about the carboxylic acids, the esters, and the amides. Okay, and we can see the difference. In aldehyde, notice carbonyl carbon is bonded to another carbon and a hydrogen. In a ketone, the carbonyl carbon is bonded to two other carbons, or two alkyl groups, like for example in acetone. As far as carboxylic acids, esters, and amides, notice that carbonyl carbon is also bonded to another electronegative atom. So in the case of carboxylic acids, we have this oxygen, the ester, we have this alkoxy group, but the carbon is bonded to the oxygen. And then for amides, the carbon is bonded to the electronegative nitrogen. So we separate these into two different groups because of the type of reactions that they undergo. And aldehydes and ketones tend to undergo the same types of reactions, actually addition reactions. So an aldehyde, this is the representation for an aldehyde, and we have the carbonyl group, and an aldehyde always has one hydrogen bonded to the carbonyl carbon, and a ketone has two of these alkyl groups bonded to carbonyl carbon, so there is no hydrogen on the carbonyl carbon. So that's how we differentiate the aldehyde and ketone. So let's start naming some of the aldehydes. Again, a lot of these compounds go by their common names. So here is the smallest aldehyde, and this is formaldehyde. And notice that carbonyl carbon is bonded to 2 hydrogens. The next one is a 2-carbon aldehyde, and it is called acetaldehyde. And then we have a benzene ring with the aldehyde group here, and this is called benzaldehyde. Now, the IUPAC rules for naming aldehydes are: first, you find the longest chain that has the carbonyl group, name it as an alkane, and then replace the E with an Al. Number the chain with the carbon that contains the aldehyde group as carbon number 1. And then we identify and number any substituents. So because in an aldehyde, the aldehyde group is always on carbon number 1, we don't have to include the number. So let's go ahead and name some of these compounds. And let's go up here. We've already seen formaldehyde, and that's the common name. But to name it using the IUPAC rules, we have a 1 carbon, that'd be a methane. We drop the E and add the Al, and this is methanal. Not to be confused with the alcohol methanol. Here we have a 2-carbon aldehyde, and this would be called ethanal. So let's go ahead and name this one here. And we start with this. This is carbon number 1. All right, so the carbonyl carbon is carbon number 1. So we have 1, 2, 3, 4, 5. That's a pentane, and we name it as pentanal. This one here, again, the carbonyl carbon here is always carbon 1. So we have 1, 2, 3, 4, 5, 6. So that's a hexanal, and we have a methyl group on carbon number 4. So that is 4-methyl hexanal. Now let's name the ketones. Common names, the most common ketone that we know is acetone. This is the simplest ketone. Notice again, in a ketone, the carbonyl carbon is bonded to 2 other carbons, so there is no hydrogen on carbonyl carbon. So, for example, here, this one here would be called ethyl methyl ketone. Actually, the ethyl comes first, so this should be ethyl. And this is the common naming: ethyl methyl ketone. Okay, so you just name the 2 alkyl groups and then add the word ketone. Okay, let's go to this other slide here. And using the IUPAC naming, what we do is we name the ketone as an alkane, drop the E, and add the suffix ONE. Then you number the longest continuous chain, beginning with the nearest end at the carbonyl group. So you want the carbonyl carbon to have the lowest possible number. So in this case here, if I number this way, it's on carbon number 3. If I number this way, it'll be carbon 4. So we have 6 carbons in the chain, and we'll name this as a 3-hexanone. Common name would be ethyl propyl ketone. Ethyl comes first because it has alphabetical priority. So practice naming the aldehydes and the ketones. So here we're asked to draw structures for heptanal. Well, that's an aldehyde, and we would draw the structure like so. I'll bring this over here. So we have 1, 2, 3, 4, 5, 6, 7 carbons, and that's the hept part. And then this is an aldehyde. Again, there is a hydrogen on the carbon, so it's an aldehyde. So this would be heptanal. Okay. Here they ask us to draw 4-methyl 2-hexanone. So 4-methyl 2-hexanone would look like this. And our longest chain is 6 carbons. And we know that it's a ketone, and that carbonyl carbon is carbon number 2. And on carbon number 4, here we have a methyl group. Now here's one. This would be a common name, ethyl phenyl ketone. Remember the phenyl group, that is the benzene ring. Okay. And so we could draw it like so. There's the carbon, oxygen, so our carbonyl group, and then we have our ethyl group. So for some reason my pen is not working very well right now. So let me bring this over here. So there is ethyl phenyl ketone. Here we have 4-methyl 2-heptanone. So I would go ahead then and draw this with my carbonyl carbon on carbon 2. So this is a ketone. And then we'll have a methyl group on carbon number 4. So here we would have 4-methyl 2-heptanone. So again, carbonyl group is carbon 2, methyl group on carbon 4. So let's look at some properties of aldehydes and ketones. They're moderately polar compounds. They have higher boiling points than similar alkanes. When we talk about similar alkanes, we mean alkanes with similar molecular weights. But they're lower boiling than alcohols. And that's because aldehydes and ketones do not experience intermolecular hydrogen bonding. There is no hydrogen bonded to an oxygen, a fluorine, or a nitrogen. So here we have acetone, a 3-carbon ketone. When we compare that to propanol, which is an alcohol, 3-carbon alcohol, and we see that the boiling point of propanol is much higher than that of acetone. And that's because, again, acetone molecules cannot experience intermolecular hydrogen bonding, so where propanol can. So that means that propanol is going to have a higher boiling point than acetone. Same here. Here we have butane, and we compare that to propanol, let's say, and butane has a much lower boiling point than propanol. That's because butane only experiences dispersion forces, whereas propanol experiences both dispersion and dipole-dipole interactions. So remember, it's those intermolecular attractions, or forces, if you will, that determine relative boiling points and melting points. Formaldehyde, the smallest aldehyde, is a gas. Acetaldehyde, that boils at room temperature. Other simple aldehydes and ketones are liquids. Those with more than 12 carbon atoms are solids. Aldehydes and ketones are soluble in organic solvents, and those with fewer than 5 carbon atoms will form hydrogen bonds with water because of those lone pairs of electrons on the oxygens. Anything with 5 or more carbons is going to be insoluble in water. So here we have a representation of a ketone or an aldehyde, and we can see that it can form hydrogen bonds with water molecules because of the lone pairs on this oxygen. So it makes the smaller aldehydes and ketones, those with 4 or less carbons, soluble in water. Just like everything else, the longer that hydrocarbon chain gets, the more hydrocarbon-like those compounds become. Simple ketones dissolve both polar and nonpolar compounds. Again, as far as dissolving the polar compounds, that'd be ketones with 4 or less carbon atoms. Again, when increasing the number of carbon atoms, the properties of aldehydes and ketones become more alkane-like. In other words, less soluble in water. They have distinctive odors. They're used in soaps, cosmetics, perfumes. And here are a couple of examples of some common aldehydes. Here we have cinnamonaldehyde. Okay, and this actually comes from cinnamon bark and is used as a flavoring in foods. And right here we see the aldehyde group. And then citronella, and we have these candles, right? The citronella candles that we burn in the summer, and we use them as insect repellents. And again, here is that aldehyde group. By the way, when writing the formula for an aldehyde, so let me just write this one here for butanal. Here we have butanal. Many times when writing out the formula, it'll look like this, and you have to realize that that is an aldehyde. If you're not sure if it's an aldehyde or an alcohol, you draw the structure, okay? Notice the only way that you can draw this would be like this, so it is an aldehyde. I just wanted to make you aware of that. Lower boiling aldehydes and ketones are flammable, can form explosive mixtures with air. Small aldehydes are toxic, and small ketones are low in toxicity. So let's take a look at this compound here, and let's look at some of the properties. First, let's name the compound. Well, it's a ketone, and it would be 1, 2, 3, 4, 5. That's a pentanone, and that'd be carbon number 3 is the carbonyl group. So that would be 3 pentanone. So 3 pentanone. Is the compound polar or nonpolar? Well, how many carbons? 1, 2, 3, 4, 5. No, it's right there at 5 carbons, so it would be nonpolar. Is it a solid or a liquid? Well, it's a liquid. Remember, you got to have 12 carbons or more for it to be a solid. Is it flammable or non-flammable? Well, I'm going to say that it's probably flammable. And would the boiling point be greater than or less than 100 degrees Celsius? Well, probably less than 100 degrees Celsius, considering that you mainly have dispersion forces here, and there is no hydrogen bonding between these 3 pentanone molecules. So I would say it's less than 100 degrees Celsius. We can determine some of the properties of these compounds by just looking at the structure. Here's a question. Why do aldehydes and ketones have lower boiling points than alcohols with similar molecular weights? That's because no hydrogen bonding between ketone and aldehyde molecules. Why do aldehydes and ketones have higher boiling points than similar alkanes? Because alkanes have only dispersion forces. Okay, there are no dipole interactions. Similar molecular weight alkanes are going to have much lower boiling points. Oxidation of aldehydes. Alcohols are oxidized to aldehydes and ketones. We already talked about that before. Aldehydes, as we know, can be further oxidized to a carboxylic acid. Can ketones be oxidized? No. Why? Because the carbon does not have an available hydrogen. So aldehydes, and we already learned this from the last chapter, can be oxidized to carboxylic acids. Ketones cannot undergo oxidation because they don't have that available hydrogen. Now, let's take a look here. We have benzaldehyde, and so this can be oxidized to the carboxylic acid. This is the carboxyl group, remember, and that's benzoic acid. So here we can take 2-methylbutanol, okay, that's butanal. Here we can take 2-methylbutanol and oxidize this to a carboxylic acid. Notice the chemical reaction only takes place here at the carbonyl group. The rest of the molecule stays intact. Okay, so 2-methylbutanol can be oxidized to this 3-methylbutanoic acid. Again, the reaction takes place at the carbonyl carbon. The rest of this molecule stays intact. Okay, so let's talk a little bit about reduction of aldehydes and ketones. And in a reduction, we add hydrogen across the double bond in order to produce an OH group. So here we have a carbonyl group, and it undergoes reduction. And notice that the carbon-oxygen double bond breaks. So remember, a double bond has both a sigma and a pi bond, so it's the weaker pi bond that breaks, and hydrogen is added to the oxygen as well as to the carbon. So reduction of an aldehyde or a ketone is going to produce an alcohol. So aldehydes are reduced to primary alcohols, and ketones are reduced to secondary alcohols. Remember, this is the reverse of alcohol oxidation. So we already talked about that in the last chapter. Let's go up here. So how does this work then? So we have the very polar carbonyl group. Remember, a partial negative charge on the oxygen, partial positive charge on the carbon. The hydrogens come from two different sources. One of the hydrogens, actually in the form of a hydride ion, will add to the carbon, and then the other hydrogen in the form of a proton, which comes from hydronium ion, will add to the oxygen. So let's take a look at this. So we have this aldehyde. We add a reducing agent. The reducing agent is going to provide the hydride ions. So that could be sodium borohydride or some other reducing agent. And so the double bond here breaks, so that pi bond breaks. The hydride ion then is going to add to the carbon. Okay, remember that carbon has a partial positive charge, oxygen a partial negative charge. And then we have acid in solution, so we're going to have hydronium ion and a proton then, right? Remember, a hydrogen ion is just a proton. That's going to add to this negatively charged oxygen here. So the hydrogen that bonds with the oxygen is from the acid, and the hydrogen that bonds with the carbon is from the reducing agent. So you need to understand that. That's why we have both a reducing agent and an acid. So let's go ahead and look at the reduction of butanol. And so we know what's going to happen here. This double bond is going to partially break. Remember, we have that partial negative charge on the oxygen, partial positive on the carbon. Okay, so when that bond breaks, all right, we have this is sodium borohydride. This is a reducing agent. This is going to provide the hydride ion. The hydride ion is a hydrogen with 2 electrons and a negative charge. Okay, so that hydride ion then is going to bond to the carbon. Okay, so that's right here. And then we have hydronium ion in solution, so it's an acidic solution, and that hydrogen ion, or that proton, then will bond here to the oxygen. So again, the rest of the molecule stays intact. So here we have 1-butanol. So the butanol is an aldehyde. Aldehydes will reduce to primary alcohols. So in this case, butanol to 1-butanol. Let's take a look at what happens when we reduce a ketone. So again, the same thing is going to happen. This carbon-oxygen double bond is going to partially break. We have the hydride ion from the reducing agent, and that is going to bond to the carbon, and then a proton from the acidic solution is going to bond to the oxygen. So in this case here, butanone is reduced to 2-butanol, which happens to be a secondary alcohol. The next type of reaction we're going to look at, remember I said these reactions that aldehydes and ketones undergo are addition reactions. We're adding to that carbon-oxygen double bond. Here we're going to look at hemiacetal and hemiketal formation. So what are these? Well, we start off with an aldehyde or a ketone and an alcohol. And what we end up with is this compound that has both an OH group and this alkoxy group, this OR group, bonded to what was the carbonyl carbon. So the only difference between a hemiacetal and a hemiketal is whether or not you start with an aldehyde or a ketone. If you start with a ketone, then we end up with a hemiketal. And this is a compound, again, that has both an alcohol-like group and an ether-like group bonded to the carbon that was once the ketone carbon. The hemiacetal is a compound with both an alcohol-like OH group and an ether-like alkoxy group bonded to the carbon atom that was once the aldehyde carbon. So you react an aldehyde with an alcohol, we produce a hemiacetal. When you react a ketone with an alcohol, we end up with a hemiketal. I will tell you right now, hemiacetals and hemiketals are not very stable. Notice we have an equilibrium going here. They're not stable, and therefore we are not able to isolate them. In this reaction mixture, you're mainly going to have the aldehyde and the alcohol, or the ketone and the alcohol. Let's take a look here. So here we're going to react acetaldehyde and ethanol. And so we can see exactly what happens here. The hydrogen, this hydrogen here from the hydroxyl group, right? We have an alcohol. So this hydrogen is going to add to the oxygen. So the carbon-oxygen double bond will partially break. The hydrogen ion will add to the oxygen here, and then we're left with this alkoxide ion, right? This alkoxide ion. Well, sorry about my pen, it's just not working the way it should be. There's nothing I can do about it right now. So you have this negatively charged ion left. So hydrogen ion from here adds to the partially negative oxygen, and then this alkoxide group here adds to the partial positive carbon, forming this. So what we have here is we started with an aldehyde, we end up with a hemiacetal, and we can see what was the carbonyl carbon now has an OH group and this alkoxy group, okay? And you can even tell when you are given the structure of any hemiacetal, you can tell the alcohol and the aldehyde that it was produced from. So how do you do that? Well, we know that this part here is the alcohol, so it's a 2-carbon alcohol, so that must have been ethanol. And then we know that this hydrogen here came from the alcohol, so you just put the double bond back here, and then this part of the molecule gives you the starting aldehyde. How do you know it's an aldehyde? Because of that hydrogen on the carbonyl carbon. Here we have a ketone, acetone, and we react that with ethanol, And again, this carbon-oxygen double bond is going to partially break. The bond between the hydrogen and the oxygen is also going to break. All the electrons will be left with the oxygen, so we just end up with hydrogen ion, and that will bond to the oxygen, and then the alkoxide group, okay, remember that's going to be negatively charged, will bond to the carbon. So we end up with this, there's the alkoxide group that added, this is the hydrogen, and this is a hemiketal. How do we know it's a hemiketal? By looking at it, because this carbon, which was the carbonyl carbon, is not bonded to a hydrogen. Okay, and remember, you can tell which alcohol and which ketone were used here. You know it was a ketone because there's no hydrogen on the carbon, and so this part of the molecule here will tell us which ketone, and this part of the molecule here will tell us which alcohol. Okay, so if I had this and I asked you, well, how was this produced? What were the reactants used? Well, I'd know that this part here, this is the methoxide group, so that would have come from the alcohol methanol. And then it's this part here that tells me what the other reactant was. In this case, it's going to be a ketone. There is no hydrogen on the carbon, and this then would be acetone. So you just need to analyze the substance. So practice those. I will have something on the exam about hemiacetals and hemiketals. It turns out that most simple sugars, here's an example, glucose, will exist in what we call a cyclic hemiacetal form. And right here it is. And then here I just drew this out so that you can see the cyclic form. And the reasons why is because hemiacetals are usually too unstable for us to isolate them. They're not stable at all. So the major exception occurs when you have these two functional groups that do react when they're part of the same molecule. We'll take a look at that reaction later when we get into carbohydrate chemistry, but it's because of the cyclic hemiacetal form being more stable that simple sugars like glucose exist in this cyclic hemiacetal form. And you say, well, wait a minute, I don't see the hemiacetal here. Well, let's take a look at this carbon right here. That's a carbon. It has both an OH group. It's also bonded to this oxygen, or you can look at this as the alkoxy group, okay? But we'll talk about these a little bit later. But I think the main point to take home is that hemiacetals and hemiketals are not very stable. So let's take a look at acetals and ketols. And an acetal, it's a compound that has two ether-like groups, two of these alkoxy groups bonded to the same carbon atom, which was once the aldehyde carbon. And a ketol, as you can guess, is a compound that has two ether-like groups bonded to the same carbon atom of what was once the ketone. So if you start off with a ketone, you're going to end up with a ketol. You start off with an aldehyde and acetal. Okay, basically we would add more alcohol to the aldehyde and ketone. We have an acidic solution and a catalyst, and of course a hemiacetal or hemiketal will form. But then when we add more alcohol, again an acid and a catalyst, now what will happen is we have the formation of an acetal or a ketol. And how can we tell that? We have those two alkoxy groups, those two OR groups bonded to the same carbon. It turns out that acetals and ketols are biologically important because of their role in carbohydrate chemistry, and we'll be talking about that later. So here we can react acetaldehyde with 2 moles of ethanol, or 2 ethanol molecules. Again, we need an acid catalyst, and so we have we have this group here, add to the oxygen. Again, the carbon-oxygen double bond will partially break, and then we have an alkoxide group, also add here to this carbon. That's the acetal. And for the acetal, notice that we have a hydrogen bonded to the same carbon that contains the 2 ether-like groups. So we know that this has been produced from an aldehyde. In this case here, again, in acetone, we have 2 moles of ethanol to 1 mole of acetone, an acid catalyst, and again, we end up with these 2 ether-like groups, okay? But notice that this carbon that contains those 2 ether-like groups is not bonded to a hydrogen. So we know this is a ketal. This has been produced from a ketone, okay? So I suggest that you look at some of these reactions and make sure that you can differentiate between a hemiacetal, a hemiketal, an acetal, and a ketal. Let's take a look real quick at acetal and ketal hydrolysis. And a hydrolysis reaction is one in which a bond or bonds are broken, and also you have water involved, and we have a hydrogen and a hydroxide ion from the water add to the atoms of the broken bond or bonds. So basically a hydrolysis reaction, it involves the breaking of bonds and then the addition of water. Okay, so let's take a look at this. This would be either an acetal or a ketal, and what'll happen here is the bonds here are going to break. So these bonds here are going to break, okay, and also the bond between one of the hydrogens and the oxygens from the water molecule, that's going to break, and so we're left with a hydroxide ion and a hydrogen ion, or a proton if you will. And so the hydroxide ion from the water is going to bond to the R group, if you will, okay. So it's going to bond to this, and that's going to form 1 molecule of the alcohol. And then the hydrogen ion from the water is going to bond to this OR group, forming the 2nd molecule of alcohol. So we end up with our aldehyde or ketone, and then 2 molecules of alcohol. Okay, so that's just, the hydrolysis is just the reverse of the acetal or ketal formation. Okay, and remember that was an equilibrium situation, so that's dictated by Le Chatelet's principle. Let's go ahead and talk about some common aldehydes and ketones. Formaldehyde. This is a gas at room temperature. It's colorless. It can cause irritation in the bronchi, the eyes, and the throat at very low concentrations. You don't need much of it. It can also trigger asthma attacks. In fact, a lot of adhesives that they use in building today releases formaldehyde into the environment. So that can be very bad for someone who is asthmatic. Formaldehyde is toxic if you ingest it. It's used for sterilizing equipment, and it's good because it kills viruses and bacteria. Its major use, though, is in the production of polymers, and as I said, as an adhesive for binding plywood, insulation, and so on. Here we have acetaldehyde, or ethanal. This is a flammable liquid, and we already talked about this acetaldehyde as being found in ripened fruits. It's certainly not as toxic as formaldehyde. Small amounts of acetaldehyde are produced when we metabolize carbohydrates. We'll be talking about that later. And in large doses, it can cause respiratory failure. And also, people that are exposed to acetaldehyde every day, mainly because of their job, exposure to this can mimic alcohol abuse symptoms. So people that work with this stuff have to be very, very careful. It's used in the manufacture of disinfectants, perfumes, drugs, varnishes, photographic chemicals, and in room air deodorizers. It's also used as a flavoring and as a food preservative and also as a fragrance. So many uses for it. Remember, we talk about toxicity. All chemicals can be toxic. Water could be toxic if taken in very large amount. So even though something might be toxic at one concentration, it might not be as toxic in a lesser concentration. So you're going to find these chemicals in, different products that we use every day. And then, of course, we have acetone, and we know it's a liquid at room temperature, and it is immiscible with water. It's also soluble in organic solvents. We use it as a solvent in varnishes, nail polish removers. It's highly volatile, and we don't really have any risks associated with acetone. This should say health risks, not healthy risks. It can produce intoxication if inhaled. That's because it's, again, very volatile. I just wanted you to know some of the properties and characteristics of some of the smaller aldehydes and ketones, some of the ones that we're more familiar with. Anyway, that concludes this chapter. I suggest that you take a look at the reactions that I talked about and study them. And if you have any questions, then you're more than welcome to contact me, and I'm very happy to help you with the material. So read over chapter 23. There are some sections that you can skip, and those are indicated in Module 4 Organizers. So have a wonderful day, and if you have any questions, please come see me.